Previously, we have seen the concept of vector space V, and more importantly, when V is equipped with inner product, we call it an inner product space. So when we talked about a vector space, we know that a basis for that vector space has members. Suppose that the vector space M V has a dimension of n. It means that it has a basis where phi1 dot 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 phi n can be a basis vectors for V if span of all the phi k's is the vector space V itself, and more importantly, phi1 to phi n is linearly independent. So loosely speaking, all those vectors are must be complete enough so that you can explain all the vectors in V. But also, not only that they have to be complex enough, flexible enough, the number of the basis vector only need to be sufficient. They cannot be more than it needed to be. So that we use that degree in terms of being independent. So this is a recall of a basis vector. So when we discuss more about an inner product space, we have seen the concept of two vectors are being orthogonal. So now the question is, are these two properties the same or not? Being independent linearly as two vectors in the vector space and being orthogonal on inner product space. Here I have some specific example for you to see first. Suppose we have V1, V2, and V3. These three vectors are independent. How can we check? The concept is that vectors are independent if we take the linear combination of them. Let me just take this, all right? Let me just take this phi. If we just take linear combination of them and set it to 0, it must implies that all the alpha 1, alpha 2, alpha 3 must be 0. And from this specific example, you will see that alpha 1, 1, 2 minus 1 plus alpha 2, 1, 0 minus 1 plus alpha 3, 1 minus 3, 4. If you set it to 0, it's gonna end up in solving linear equation and multiply it alpha 1, alpha 2, alpha 3. And if you solve this equation, you will find that this matrix has an inverse, right? You can check that the determinant is non-zero, and so it means that when you solve all the alpha, they are all 0. So these three vectors are independent. However, if you check the inner product between two of them, for example, 1 times 1 minus 1 times minus 1, the inner product is 2. These two guys are not orthogonal. Also, these two guys, 1 is 1, minus 1, 4 is minus 4. Totally, inner product is negative 3. So these two guys are not orthogonal. In this specific example, we have found three vectors that are independent, just like this one, but they are not orthogonal. They are not orthogonal. You can see that. I have these three examples that they are orthogonal. You can check. Inner product is 0. Inner product is 0. They are orthogonal and they are independent because if we check the dependency using the same concept, you will find that they are independent. However, this phi one is norm is 1. This one is norm is 2, square root 2. This one is norm is square root 2. So if the vectors are orthogonal, but I can always normalize the vector so that it has a unit norm. For example, for phi2, I can define phi2 such a way that I normalize it norm. So the norm is square root 2, so I normalize it so this way. you can see that the phi tilde now has a unit norm. So we may wanna get we may be interested in a set of vectors that are not only they are not not only that they are orthogonal, but also have a unit norm. Okay, so these three properties that we have it in hand now. We have this important fact that if three vector if you have a set of orthogonal vectors, those vectors are always independent. Why? Because now if phi1, phi2, phi m are orthogonal, right? But if we want to check whether these guys are independent or not, you will start with alpha 1 phi 1 plus alpha 2 phi 2 plus the dot alpha n phi n equals 0. And you wanna show that alpha 1 equal alpha 2 dot equal alpha m is 0, right? I can start with this equation and I say that how about how about I take inner product with phi 2 with phi 1, sorry, with phi 1. So when I take inner product, I'm going to get alpha 1 phi 1 phi 1. And then but when I take the other inner product, I would get I would get 0, right? Because my let me just write it down and say it at once. Okay. Because I take inner product with phi 1, but inner product of phi 1 with other phis would be 0 because they are orthogonal. So from the first equation, I have alpha 1, the norm of phi 1 square equals 0. But my phi is not a 0 vector, then I must have alpha 1 equal to 0 instead. And next, I can do the same way. I can take the inner product of the whole equation with phi 2, and I would get alpha 2 equals 0. And I repeat this process, and then you will see that all the alpha k's are 0. And that's a proof of how all the orthogonal vectors are independent. And obviously, the converse is not true by this specific counter example. Okay. So, what we have seen when we study about the linear space is a process of finding a basis set or basis vectors for a vector space. Now, if we want to put more properties on those basis vectors, not only that we want it, we require it to be linear independent, but you would like to enforce orthogonality property on it, and also the unit norm property. So we say that a basis set is an orthonormal set if all the phi I and phi j are orthogonal, right? And they have a unit norm. So, okay, when the inner product of phi 1, phi I, and phi I is going to be all 1. Okay. Um, the thing is, how can we construct an orthonormal basis set when you have just a basis? Here we get some example of the result. These phi, if you can check that they are mutually orthogonal, all right? This orthogonal with this, phi 1 orthogonal with phi 3, phi 2 orthogonal with phi 3, and all the phi j's have a unit norm. In order to find an orthonormal set, orthonormal basis set, maybe we would like to maybe explain the benefit, right, or the advantage of having an orthonormal set. Let me skip to this page first. Because if phi k is an orthonormal basis for vector, um, now I'm going to compare it with v1 and v2. Okay, so suppose this is just any other basis for v. If we want to represent x in a vector v, we know that x is alpha 1 v1 plus alpha 2 v2 blah 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 alpha n vn. And you know how the drill, how to find how to represent X as a linear combination. The thing is you need to find alpha 1, alpha 2, and alpha n. All right. For example, if we talk about R2, I can say, please verify that these two guys are linearly independent. But if I ask you what my X, which is 5 and 4, what is my representation of the vector 5, 4 in as a linear combination of this? I must be write it as alpha 1, 1, 1 plus alpha 2, 2, 1. And then I need to solve it. And then I need to solve the equation for the left hand side is 5, 4. I need to solve for alpha 1 and alpha 2. Okay. Now let's use the orthonormal basis set. If I have orthonormal basis set, orthonormal basis vector phi k, I can do the same. I can say I can claim because they are basis. I can say my x is alpha 1 phi 1 plus alpha 2 phi 2 dot 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 alpha n phi n. But now, when I'm about to find phi k's, when I want to find the coordinate or the representation of x with respect to these bases, notice that I can just, if I want to find alpha 1, I can take inner product of x with phi 1 on the left-hand side, and on the right-hand side will be very simple because the inner product of phi 1 with all of these guys will be 0. So my alpha 1 is x, inner product of x with phi, and inner product of phi with phi. Moreover, if my orthonormal, because my basis vector are orthonormal, not only that they are orthogonal, but they have a unit norm. So these phi 1, they have a unit norm. So that's why the result is the the coefficient alpha 1 is just x inner product of x with phi 1. So that's why we have the orthogonal expansion. If you want to represent any vector x in onto the orthonormal basis, the coefficient is very simple. Just take inner product of x with each of the basis vector, each of the orthonormal basis vector. So this is the motivation of why this is to explain why it is useful to have orthonormal basis set. So come back to the question. If I have only a basis, maybe a standard one, maybe the one that are they are only linear independent but not orthogonal, we can apply what's so-called Gram-Schmidt algorithm to find an orthogonal basis vectors. So Gram-Schmidt algorithm goes like this. The setting is you have a a set of vector A's, A1 dot dot AP. You have P vectors. The goal is GS algorithm. The Gram-Schmidt will find orthogonal vector Q1 dot 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 QM. Uh, Q1 until QM, we have such property that your original vector A will be a linear combination of all those Qs, and vice versa, which means Q is also a linear combination of all those A. Okay. If the j minus 1 vectors are independent, but when you include the additional 1aj, they become dependent, the Gram-Schmidt algorithm will detect that uh, the first aj that is a linear combination of the previous one. So if you adding aj to the set and they become dependent, which it means that these aj must be linear combination of the previous ones. And in order to achieve such goal, the Gram-Schmidt algorithm goes like this. Okay, we're gonna start with let me explain on the diagram. Okay, and we go over an example. In the diagram, what I'm gonna have a unit norm ball. So this is to describe a set that any vector has a unit norm. Okay. Suppose you have our original vector a1, okay? What you're going to do is that you're going to pick a2, okay? Sorry. Suppose you are given by two vectors, all right? The first step is q1 TUD is going to be in the same direction as a1, but you're going to normalize it. From q1 TUD, you normalize it so that it becomes q1, becomes inside the unit norm. Next, you pick the next vector, the next input vector, which is a2. And what you're going to do is that for a2, what you're going to derive is q2 TUD. Q2 TUD is going to be the residual after the projection onto the previous k minus 1 vectors. In this case, this is our second step, right? The previous orthonormal vector is only q1. So what you're going to do is after you project a2 on q1, we take the residual. So, all right. So your A2 is here. If you project it is here, but we take the residual. The residual is assigned as Q2 TUD. Okay, Q2 TUD. So what is the projection again? Let me write it down. How you define the projection? So the projection of A2 onto Q1 is supposed to be A2 inner product with Q1 and multiply with Q1. You don't need to normalize it because Q1 is already have a unit norm. Okay? Okay. So so this is that portion, okay? That portion. So the residual, what would be the residual? The residual would be A2 minus A2 inner product with Q1 and Q1. This is what you're going to take as Q2 TUD. Next, your Q2 TUD doesn't have unit norm. You normalize it, not divide it by its norm, and it becomes Q2. Okay. So if you have more than two vectors, you continue. You continue. All right. In R3 it's gonna be suppose because we draw on the paper, so it means that we explain things on R2, and on R2 you can only have at most two vectors that are orthonormal. So but the process goes like this. The next step is suppose you have more than two, right? More than two input vectors. The third vector, you're going to, suppose you have A3, you're going to project A3 with Q1, right? You're going to project A3 on Q1 and you project it on Q2. So this is a portion you project A3 on Q1. This is a portion you project A3 on Q2. So after you subtract on A3, this is the residual. So you assign it as Q3 TUD. And Q3 TUD, you normalize it. You normalize it so it becomes Q3. And you keep repeating this process. So let's go one step more. Q4 TUD is gonna be A4. You take A4, the next input vector, and subtract by the projection of A4 onto the previous k minus 1. So it's gonna be A4 with Q1, A4 with Q2, and A4 with Q3. This is the residual after the projection onto the previous k minus 1. And then once you get Q4 TUD, you normalize it. You normalize the norm. So it becomes Q4. Okay? Until all the input vectors are processed. If you found that Q3 TUD, if you found that one of the QK TUD is 0, if you found that, what does it mean? If the residue after the projection is 0, it means that your AK is a linear combination of the previous k minus 1. So it means that your AK is dependent on the previous vectors. Okay. So let's see some numerical example that I prepare. Okay. So the question is this. I have a vector space V that is spanned by 1, 1, 4, 5, all right, minus 2, 1, all right, in this example. And let me call it A1, A2, A3. You may notice that you have three vectors. You know beforehand that one of them must be dependent of the others because we're now in the subspace of R2. Okay, but let's see how the Gram-Schmidt algorithm would detect this dependency. Okay, so let's start. So the first step of the Gram-Schmidt is Q1 TUD is A1, which is 1, 1. Okay, but it doesn't have a unit norm yet. You normalize it so that it becomes Q1. So Q1 is going to be square root 1 over square root 2, 1, 1. Okay, next Q2 TUD is to take the next input vector A2 and you subtract by the projection of A2 onto the previous Qs. Now you only have one Q, you project it on Q1. Okay, so that's going to be 4, 5 minus 4, 5 inner product. Oh, this is to multiply with Q1. 4, 5 inner product with 1, 1 square root 2 and multiply with Q1. So 1 over square root 1, 1. That's going to give you 4, 5 minus 1 half. Let's compute the number, the value. What is the inner product of these guys? So I get this 1 square root over 2. This is 1 half. So inner product of this guy is 9, right? And then and then 1, 1. So the result of this matrix is this vector. Calculate everything. I'm going to have minus 1 half and 1 half, all right? So you can see real quick that it doesn't have a unit norm. So my Q2 is going to be, you can think of this as, oh, it's in the direction of minus 1 and 1, okay? And you normalize it. So it's going to be 1 and minus 1. Okay. Next, Q3 is to take the and let me highlight the result. Let me highlight the result. Sorry. Q3 TUD is going to be A3. Subtract by projection of A3 onto the previous Qs. We have the previous two vectors, so it's inner product with of A3 with Q1 times Q1 minus inner product of A3 with Q2 and multiply with Q2. So let me just calculate the number for you. So it's 2 minus 1. Okay. And 2 minus 1 and Q1. So it's going to be 1, 1 square root of 2 times Q1 minus 2 minus 1 transpose. I forgot the transpose because this is inner product, right? Q2, what do I get? I get 1 minus 1 times 1 of square root 2 times Q2, which is 1 over square root 2, 1 minus 1. Okay, let's calculate the number. 2 minus 1. I get 1 half here, 1 half here, and the inner product would be oh, sorry. This is supposed to be minus 2, 1, okay? Minus 2 and 1. Let me just change. Minus 2 and 1. Okay, minus 2 and 1. So the inner product here is minus 1, and this is 1, 1, right? And and 1 over square root 2 is 1/2 here, and the inner product here is negative 3, and multiply it with 1 and minus 1, okay? Just calculate the number. It turns out that the result is 0. And that is supposed to be when one of the QK is 0, it means there is no residual left. It means that A3, when you project it on the other two axes, on the previous vectors, all the components in A3 are already can be explained. They can be explained by Q2 and Q1. Therefore, A3 is independent of Q1 and Q2. Then to select orthonormal vector out of the Gram-Schmidt, you select only you only select the orthonormal one. You select only the non-zero Q1 and Q2. So when we find this, the new basis is gonna be 1, 1 and 1 square root 2, 1 and minus 1. Okay. Gram-Schmidt algorithm is already implemented in the software as well, but all the basic principle is what we describe here in this video. Okay. Yeah. So it's a process of finding orthonormal basis set from the original set of vectors. Okay. You can apply this for not only Euclidean space, but can be also anything that are inner product space as well.